So theorem, I'm just going to state whatever we have arrived at for an ergodic finite state DTMC. There is a unique stationary vector pi such that limit n tending to infinity Pijn equal to pi j for all j equals 1 to m. Or this can be rewritten as limit n tending to infinity p to the n is equal to write as 1 1 1 1 1 times the row vector pi. Alright, so if you call this column vector of 1s as e, this is just e pi, the notation of our book. Alright, so the n step transition probability matrix converges to e pi, the rows of all pi's. Alright, further, the above convergence is geometric in n. What I mean is that this limit is reached geometrically fast in n, right? Because you have that 1 minus 2 beta over to the n type of a behavior, right? So that is the result that we have proven. Note that we have not explicitly proved uniqueness, which can also be proved in a fairly straightforward fashion. If you look at this proof of this theorem which I just stated, this is the theorem that I just stated. And the proof is here. Uniqueness proof is here. So if you take any other mu and say that there is another solution mu that you converge to, then that mu, we know that mu has to satisfy mu p equals mu, right? This we argued earlier using Chapman-Putnam. Alright, so then you finally end up proving that in this step you end up proving that mu has to be equal to pi. That's because this mu e, right, is equal to 1, right? That is the issue. Mu e is equal to 1. So let me just to just clarify this. Pi is the limit of the maximum over pi j is the limit over limit n tending to infinity max over I, which is equal to limit n tending to infinity min over I. Right? I'm just calling this pi j. Is this the same pi j which satisfies pi is equal to pi p? The answer is yes. That's what I'm proving. That's what is being proved here. Alright. So there is this unique solution to pi is equal to pi p, and that is the limit of this p to the n. That's what is proved in this theorem. Okay. So this theorem is sometimes known as Frobenius theorem for Ergodic Markov chains. Alright. So we have come very close to what we wanted to prove, right? So far, we started with any finite state DTMC. We said that the max over each column is decreasing as n increases, and the min over each column is increasing as n increases in the matrix P to the n. Then we considered the special case of a strictly positive matrix P and showed that this decrease and increase are exponentially fast, and therefore there has to be a common limit, right? Then we considered any ergodic Markov chain, not necessarily with P strictly greater than 0, and then we said that some power h of p to the h must be strictly positive because there are only finitely many states in this ergodic chain. Then we applied that previous result to the matrix p to the h, and we obtained what we want. Basically, we proved that p to the n converges to the matrix with all rows pi, and this convergence is exponentially fast. Right? Now, there's only one step remaining in what we actually wanted to prove. So, what if we have a ergodic unichain? What does that mean? You have an ergodic class, but there could be some transient states. Right? That is the result that we finally want to prove. So far, we have gotten as far as having just one recurrent aperiodic class, or basically the entire Markov chain consists of an ergodic class. If you allow some more transient states, then we should still be able to prove that p to the n converges to pi. Now, the question is, what pi does it converge to, right? See, if you start in the single recurrent class that you have, you are going to be inside the recurrent class, all right? And the situation is exactly like the previous situation for what we just proved for the frobenius theorem, right? However, if you start in a transient state, the question is what happens, right? Transient states, by definition, you will stay in the transient state only for a finite amount of time. So you get out of the transient states and get into one of the recurrent states, and you keep going inside the recurrent state, right? In that situation, what happens is, in some finitely many steps, once you get out, then the behavior is covered by Frobenius theorem, right? And for transient states, you basically have zero stationary probability. That's what happens, right? So this is something that we can show. So if you have an ergodic unichain, this is step 4, I guess. So we have an ergodic unichain, right? Which means that one ergodic class plus some transient states. Okay, then what happens is the question. See, then I can write out the transition matrix P as follows. See, there will be a recurrent component. See, there will be a component here, which is the, let me call this PR, right? These are transitions between the recurrent states, all right? And then there will be, let's say these are, so I'm saying that these states are all transient. I'm saying, and then that these states are all recurrent. So these are transients, and these guys are recurrent. So let's say this is PT, right? These are transitions between transient states. Okay, and this is transition between transient states to recurrent states. However, this part of the matrix has to be 0. Why? Because you cannot go from a recurrent state to a transient state. It's against the definition of a recurrent state, right? So this will be the structure of the transition probability matrix of an ergodic unichain with some potential transient states. Now what happens is, so this part is covered by Frobenius theorem. Okay. Now we just have to show that if I start out here, right? I mean, I will not. If I start out in a transient state, I will eventually get to a recurrent state, and I will be covered by Frobenius theorem. That is all that I have to show, right? So this can be done as follows. So what you can do is, so let's say there are, T transient states. And let I be transient. Okay. So the point is, so if I start at I, which is a transient state, okay, there must be so there are only T transient states, right? So there must be a probability that in t steps there should be a positive probability of getting out of this transient state, right? Which means that if I sum over all the transient states, I is transient, remember, the probability of starting at a transient state I and still remaining in one of the transient states must be strictly less than 1, right? There's a positive probability, there are only t transient states after all, so there's a positive probability of going from I to some recurrent state. And once you get to the recurrent state, you're never going to come back, right? So this is true for any I which is transient, right? So if you look at max over I belongs to t, and you take that sum over j belongs to transients, Tij t, this also has to be strictly less than 1, right? Let me call this gamma. Alright, this gamma is something strictly less than 1. Then what we can show is a lemma like this. You can show that max over L belongs to transients, sum over j belongs to transient, Plj n less than or equal to gamma power gamma raised to n over t. So what this is saying is that if I am, so this is very easy to prove because I have a probability of less than 1 after t steps that I am still in a transient state is strictly less than 1, right, which is gamma, right? So if I keep giving you very large n, there is a probability that I still remain in a transient state, right, after a very large n. So that's what this probability is, right? That has to decay geometrically fast again, right? This is the lemma that that you can easily prove using this property, and that if you look at this in Gallagher's book, so he explains the structure of this matrix, and the lemma I'm talking about is this one, which is just a pure algebraic manipulation that's done. Okay. Then you can actually go ahead and prove that. Then you can prove the result you want. Okay. Next, you proceed to the case where the initial state is some transient state I, right? And then you go to some recurrent state j, which j in R, right? J is which is recurrent. So what you have proven so far in that lemma is that, so in this previous lemma you have shown that the probability of still being transient after a large n number of steps goes down exponentially fast, right? So there is overwhelmingly less probability or overwhelmingly high probability of being in a recurrent state once you start in a transient state, alright? So once you get to a recurrent state from a transient state, then you can again look at this Chapman-Kolmogorov equation. You start with any I which is transient and any j which is recurrent, and you look at Pij 2n, which by Chapman-Kolmogorov, this is just Chapman-Kolmogorov here. You can write out this equation. You are just splitting the sum over different transient states and different recurrent states. Okay. So then what you do is you have upper bounding and lower bounding. Okay. So here you are just looking at the max. So you are just replacing Pkj with the max. Okay. And you get that term. And likewise you are just replacing this term with the min, and you are getting this kind of a term, right? So you get this lower bound and upper bound on Pij 2n. Okay. Now in the recurrent Markov chain corresponding to PR, let pi j be the steady state probability. Okay. Then we know from the previous consideration that this pi j lies between the maximum and min over L of PLJN. Okay, so this is like previous reasoning. So you will get Pij2n is less than or equal to. So this is like step 3, right? And this is what we have proven in this lemma here, this guy, right? So you will get that the difference between Pij2n and pi j decays geometrically fast, and therefore you will have convergence. Okay, so that is what you get here. So we can just state a theorem. So what we have proven, I would rather walk you through this proof in Gallagher without writing everything out in great detail, is that we can prove the following theorem. So essentially what you're proving is that if you start in a transient state, you get out of it exponentially fast and you get into a recurrent state, and after you get into a recurrent state, Frobenius theorem applies, right? So and then you converge exponentially fast to pi, right? So the theorem that you can state is the following. This is for ergodic unichains. For a finite state ergodic unichain, limit n tending to infinity e to the n is equal to e pi. Like remember, this e is just the column of ones, and pi is just pi 1 dot 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 by m, alright? Pi capital M is the name states. So this is the matrix of, this is nothing but your matrix of rows pi, alright? Where pi is the stationary distribution of the recurrent class expanded with zeros. For each of the transient states. The unit. Further, the convergence is geometric. This convergence, this limit n tending to infinity convergence is geometric in n. Alright, so if you go back to the matrix, so it looked like this, right? If you look at, so this was PR, right? This was PT, this was 0, this is PTR, right? This is how the P looks, right? The pi will, so this PR has a pi vector, right? So the pi will correspond to 0, 0, 0, as many as there are transient states. And then there will be the pi r, right? You can look at this pi r as the vector of pi's. So you can look at this as, now we start with pi r1, pi r2 and so on. So basically I'm looking at, so these are r1, r2, these are the recurrent states, right? So on till pi r, I don't know how many, there may be, let's say little m recurrent states. Okay, that's what happens. So you have, for the matrix PR, which is the recurrent component, you have a pi, right? And the pi for the entire ergodic unichain will be just 0 augmented wherever there's a transient class, and the rest of the pi is just copied from the steady state probability or the stationary probability distribution of the recurrent class. Okay, and the convergence, of course, is geometric in n because we showed this equation, Right? This equation shows that the convergence is geometric. All right. So what we have shown is that if you have a finite state DTMC, which is an ergodic unichain, in other words, if you have a single recurrent aperiodic class plus some transient states possibly, then the long-term behavior of this Markov chain is that P to the n, the n-step transition probability matrix, converges to a stationary vector, which is a solution to pi is equal to pi. Right? So this is where we have answered A3 basically in what we wrote down. Okay, and we stop here for today.